Alright guys, let's go ahead and start talking about float on. This is a lecture where we are going to talk about distinguishing between intensive and extensive properties, and we're also going to use the equation density equals mass over volume. So I'm going to talk about these two things, starting off what we already know. What we should already know, that objects will sink or float depending on their density. So we know that lighter density things will float to the top, and then heavier density things will be towards the bottom. We should know that the density of water is 1 gram per cubic centimeter. This unit can also be written as gram per milliliter, same unit. And that density can be calculated using this formula. We've probably seen this before in other classes, either in middle school or you've seen it previously in high school. When we're doing this, what we learned in the lab, modeling clays vary depending on how much modeling clay was used, so not everybody made the same shape. The volume of the modeling clay varies depending on how much modeling clay was used. So if you made a bigger shape than somebody else, then it had more volume to it. But density does not vary as mass or volume changes. So even though the modeling clay was different sizes and it had a different mass and it had a different volume, density didn't change, and it should have been the same for all the shapes that we made. So this brings us into the intensive properties. What they are properties that change as the amount of substance changes. So what we're talking about here is, when we're looking at this, mass, for instance. When you had more of that modeling clay, that means that you had more mass. So the more you added to it, the more mass that you had. This is really particularly helpful in quantitative analysis. So if we're looking at how much of something we have, and we see that mass is one way that that will vary. That's an extensive property. The other extensive properties that we should have: length. So when you're measuring something, the more you have of it, the bigger it's going to be, the more length it's going to have. Mass, obviously, we talked about that. More modeling clay, more mass. Area, since it's a dimension, it's a measurement of 2 dimensions. More of it we have, the more area you have. Same thing with volume. It's just the 3-dimension length, it's a measurement of 3 dimensions of length. And then weight, which weight is just the force of gravity caused by Earth. Think of some other ones and see if you can come up with any for class tomorrow when we talk about it. Go through the interactive practice. The other property that we have is intensive properties, and these are properties that remain the same as the amount of substance changes. So when we were talking about this, yes, if we added more modeling clay, then we would have more volume. If we added more modeling clay, then we would have more mass. But it didn't matter how much modeling clay we had, we would still have the same density for that modeling clay. Some other properties, and you can kind of see this is just a really good example. They call this a density column, and that is where you're going to have different substances at different densities. And so density, they all layer out into the densities that they have. Well, it doesn't matter how much of each one of those substances we have, it would still be at the same level in the little tube that they have here. Looking at some other intensive properties, boiling point and melting point. It's the point at which that matter is going to change states. That will stay constant. That doesn't change. If we have a gallon of water, or if we have a single 10 milliliter test tube of water, it's still going to have the same boiling point and melting point. Some other ones that we have: specific heat capacity. We'll talk about this a lot more when we talk about thermodynamics. That's the energy required to change temperature 1 degree. Malleability, so how malleable something is. Gold will have the same malleability, the ability to hammer into shape without breaking, meaning making it a very thin sheet, no matter how much gold you have. Ductility, that's the same thing, except you can draw it and just long thin wires. And then we have other ones like solubility, pH, color, viscosity, reactivity, and conductivity. We have all of those, and those are all intensive properties. So it doesn't matter how much we have, those properties are going to be the same. Now, jumping into our first example question, it says, which of the following properties can be described as extensive properties? So we're looking at extensive properties here, and that means that matter matters. Basically, however much we have, that's going to tell us what type of property it is. So when we're looking at this, we know that volume, yes, that's going to be an extensive property. Density, doesn't matter how much we have of it, it's still going to be the same, so that's intensive, so that's not it. Mass, we know that mass, definitely, the more we have, the more massive something is. And then boiling point reactivity, we know that those are intensive properties. Moving on to our next example, it says, which of the following properties would be best in determining the identity of an unknown substance? When we're looking at these, you got to think of, if we have a little bit of it, how can we tell the difference? Boiling point would be very good. It's going to be an intensive property. It doesn't change for how much you have, but it is unique, and it is specific to a specific substance. So if we have 1 gram of water or 1,000 milliliters of water, it's still going to have the same boiling point. And boiling point's a really good thing to help us determine what something is. Now, mass, on the other hand, I could have 10 grams of water and 10 grams of isopropanol alcohol, and just by looking at the mass, you couldn't tell the difference. Same thing with weight, same thing with length, and same thing with volume. So these extensive properties would not be good in identifying an unknown substance. And our last example. We see that a forensic pathologist obtains a sample of an unknown chemical taken from the home of a murder suspect. The sample initially, which is 100 milliliters, spills as it is being transferred to the lab, leaving only a 5 milliliter sample. What properties can be analyzed by the pathologist and hold up in cross-examination? So when we're looking at this, they lost 95 milliliters of that sample. They lost the majority of that sample. So since they lost the majority of it, all properties that depend on the amount of matter of that material are invalid. They can't use that. So they can't use any extensive properties to talk about it. They have to use intensive properties, and that's what they're going to have to look at. And that's going to be the things that are going to be able to hold up under court. Now, jumping into density. We talked about density a little bit. That's what our lab was about. Objects can be identified by the ratio of your mass and your volume. Density is constant for all homogeneous mixtures. And so basically anything that keeps, and we'll talk about mixtures a little bit later, but anything that's mixed and it's basically one continuous thing, then it's going to be the same density for it. And we can see that, again, this is a great example of a density column. And it's just, we're looking at our mass, looking at our volume, and that will give us our density. We get density from the equation, the mathematical equation, where we have density, mass, and volume. And this is the equation that we use to calculate density. So the definition of density, it's just the degree of compactness. It's the ratio of mass versus volume. The SI unit for it, it's a little bit different. The SI unit is kilograms over meters cubed. But in chemistry, since we deal on everything on a very small level, we are going to use grams per cubic centimeter, or which the same thing is grams per milliliter, and that's calculated. And then our volume, we have the definition there, and we either get this from using a meter stick to measure it if it's a good shape that we can actually measure, it's consistent, or a graduated cylinder by doing water displacement. And then lastly, mass is measured either by triple beam balance, but what we use probably in our class is probably a digital scale. Okay, jumping into this question, it says you place a solid piece of iron into a specially designed beaker. The beaker is then put over a very intense flame. Describe the density of the metal as the heat is continually added to the iron. So when we're looking at this, As we add heat to it, it's going to move from a solid to a liquid to a gas. And what we'll see is that basically the density will become smaller. Okay, so basically we increase the heat of the metal will it'll decrease the density of the iron, and so the density will become smaller, and the iron will have basically it'll go where the particles are really compact in the solid to moving to a liquid where it's a little bit more spread out. And so what we see is that the volume is going to increase a lot, and then moving on even more to gas, and the volume is really big, and so the density just becomes smaller, it decreases. Moving on to the next example, it says the following data is taken from the lab, that we have this cylinder here, and it wants us to what's the density of the unknown object. And so we have our height, we have our diameter, and we have our mass. And remember, density is going to equal our mass all divided by volume. So since we have our mass, which we know that will go right there, all we need is our volume. And if we look at this, we know that this object here is going to be a cylinder. And so when we look at this, the equation for the volume of a cylinder equals pi r squared times height, and that's going to be our equation for it. We have our diameter, so all we have to do to find the radius is just divide by 2, and so our radius is going to be 6.1, and we just plug everything into that equation, and we get our volume, pi times our radius, which is 6.1 squared, times a height of 20.05. We add that, or we multiply that out, and we get a volume of right around 2343.82, and that will be our volume. And when we have that, we plug everything in, mass divided by volume. It'll give us a density right around 0.222, and that's grams per cubic centimeter. And so that's going to give us our density. Moving on, we see the states of matter. There are 3 common states of matter that we see every day. There are 6 recognized states of matter in the scientific community, and these states of matter vary depending on their density. So solid will have the highest density, and then we will move up to throughout those states of matter, and the density will decrease. Now, a solid, we should know that it's a state of matter in which objects have a definite shape, a definite volume, and very limited movement of the individual particles, meaning you're actually going to have particles that stick really close together. They still move a little bit on the molecular level, but they don't move that much. It's generally the most dense state. There are some exceptions to that, and that's obviously water is one of those. We see that ice floats in liquid water, so we do have some exceptions, but generally it's the most dense state. Then we have liquid, and that is a state of matter in which objects have an undefinite shape, so undefined shape, and we have a definite volume. And so that's where we have free movement of individual particles. It's less dense than the solid state, with, of course, the exception of water. And the next one I know you're thinking about is gas, so solid, liquid, gas. Before we talk about gases, we really need to talk about the kinetic molecular theory. Now, what the kinetic molecular theory is, it's basically, it talks about how molecules move, and we use this to describe gases. And what we have is, we have to better understand gases to get an idea of them. We have 5 postulates that we stick to when we're talking about the kinetic molecular theory. Number 1, that a gas consists of small particles traveling in a straight line motion and obeying Newton's laws of motion. And so The next one we have is molecules of gas occupy zero volume. We actually know that they occupy a little bit of volume, but again, we have to use these postulates to better understand what real gas behavior acts like. Number 3 is collision between gas molecules have zero energy transfer. So basically, as these molecules come together and they collide, they still contain and hold the same energy that they came in with. And so there's no loss of energy when they hit each other. There is no attractive or repulsive forces between the molecules. So as these molecules get close together, they don't push on each other, and so they just don't repel and they don't attract each other. So they don't come together faster and they don't push each other away. And then we see lastly that the average kinetic energy of a molecule is defined by 3/2, and this is a Boltzmann constant times temperature. We can also say that the kinetic energy is also equal to 1/2 our mass times our velocity squared. And basically what this does is it allows us to say that the kinetic energy in a system is related to the temperature of a system. So basically, as the temperature goes up, kinetic energy goes up as well. And so we use these postulates of the kinetic molecular theory to help us better understand gas behavior. Now, what a gas is a state of matter in which an object has an undefined shape, an undefined volume, free movement of those individual particles into less dense than the solid and the gas state, or solid and the liquid state. The gas is going to be the least dense of what we see on a daily basis, the three main ones that we see. Now, another form of matter that we have is plasma. And what a plasma is a gas that has the electrons removed, so it has an undefined shape but a definite volume. When we think of plasmas, we can think of particles in the sun, but basically there's free movement of individual particles, and what we see is basically it's when an electron has been removed that it's become ionized. And next we'll talk about our phase transitions. So it's the changing the energy of a substance can change its phase. So as we add energy to a system, what's going to happen is the particles are going to move more, and that means that they are going to change phase. We increase their temperature, we increase their kinetic energy, they move more and they change phases. Going from a solid to a liquid, we know that that's melting. Going from a liquid to a solid, we call that fusion, or you can just call it, the more common term is just freezing. Going from a solid to a gas, so skipping over that liquid phase, we call that sublimation. You can see that when you're talking about dry ice, solid CO2 will go straight into gaseous CO2. That's called sublimation. Then we go from a gas to a solid, we call that a crystal lattice formation. And from a gas to a liquid, we call that condensation. And from a liquid to a gas, we call that vaporization, or the more common term, it's just boiling. Now, moving on to some definitions. In this one, it says that entropy is the measure of disorder in a system. And it says which phase of matter has the lowest amount of entropy. So when we're looking at the lowest amount of disorder in the system, we'd have to say that that's a solid. The solid has the lowest amount of entropy because the particles have limited movement. It has a defined shape and a defined volume. And so what we see is that because it's very, very limited, there's not a lot of disorder in it. And so it basically has the lowest entropy, the lowest disorder. The next one, we see that the kinetic energy is the energy of movement. Which molecule will be moving faster? Dichloromethane molecule at 100 degrees Kelvin, or a dichloromethane molecule at 200 degrees Kelvin. And see, we have them moving, and we have to think of the movement, so we have to think of the kinetic energy. Now remember, we talked about that temperature is going to be related to the kinetic energy. And since they are the same molecule, and we've already said that the kinetic energy equals that 3 all over 2 kT, which it also equals 1/2 the mass times the velocity squared. And so basically, the more kinetic energy they have, the higher the temperature is, the more it's going to move, because it's the exact same molecule. It has the same mass, so therefore whatever's has the higher temperature must be moving faster. So the 200 degree Kelvin dichloromethane molecules will be moving much faster than the 100 Kelvin. And our last example, it says a gas follows the postulates of the kinetic molecular theory. We call those, when it does that, we call those an ideal gas. Whereas most gases are real gases. Basically, we use those to describe gases to try to better understand them, but we really have real gases in real life. So describe the behavior of a real gas based on your answer on the postulates of the kinetic molecular theory. So basically, the kinetic molecular theory is a perfect situation. Real gases, well, number one, they do not obey the laws of motion, but instead obey quantum mechanics. Next, molecules can occupy a very small volume. We said that we just say that they don't so we can better understand it. Number three, energy is always transferred between molecules in a collision, even if by a small amount. And then molecules are attracted and they repel each other based on the charge of each one. And we can calculate our kinetic energy. And so we use a kinetic molecular theory to try to describe it as best we can, but real gas behavior in real life is a little bit different than what we like to put ideal gases in.